Hello folks, welcome to another Tesla Model 3 rear drive unit update video. So in today's episode you're going to see me fail. Yes, that's right, we like failure as much as we like success. So we are going to fail to make this drive unit spin in closed loop mode today. But like a lot of things, this will bring us one step closer to success. Now, number of things from the last video on this that I just want to address quickly before we get stuck in. The first is as to why I'm using this Toyota Prius inverter. Let me answer that question with a question. If you found yourself needing to run a completely unknown motor, you have no information on it, nobody is willing to give you any information on it, and the method that you are going to use to run it, you have never used before, it's a fairly new method, and you don't know anything about how to use it. Given those circumstances, would you A, perform said testing with a, I suppose, irreplaceable high-end Tesla inverter that will probably explode if you look at it sideways? Or would you B, use a cheap and readily available Toyota Prius inverter which happens to have anti-explosion technology built in? So answers in the comments section please. Now, secondly, and it kind of leads on from that question, we are actively working on reverse engineering the original inverter for this drive unit and have designed a little board to fit into it. I will show you that later on. But for now, our mission is to get all that exploding inverter stuff out of the way with the Prius version. Okay, that makes sense? Alright, now, how we are running or trying and failing to run the motor today is with the new field orientated control firmware that Johannes has just made available for the open inverter system. Now, I've never used it before until literally, I guess, yesterday. And it was as well that I was using the Prius inverter with anti-explosion technology because the first time that I turned the thing on, it tried to go to infinite current. Of course, the Toyota engineers had already, I guess, figured out that a muppet like me would probably do something like that, and it just went click. Whereas the Tesla inverter would have went boom. So, there we go. Right now, I've been doing some testing with the field orientated control firmware. And while I can get the motor to hop and jerk and jump about a bit, I cannot get it to spin properly. So, I started doing some investigations here, and I did have some rather crazily stupid noise prone resolver leads here, so I got rid of those and we're now using the original Tesla resolver cables going into the Prius inverter. Got these cables here for our 3-phase power. I've got them tied together so that we don't have any loops in them, because remember folks, loops radiate. Loops bad. Unless you're making antennae, then loops good. Right. So, confusing. We have 80 volts worth of DC going into the inverter. I don't have any coolant going through it at the minute. So it is shutting down sometimes when I try to put, 350 amps into the motor. These cables smolder a bit, and then the heatsink gets up warm, and even though I try to ignore the heatsink temperature sensor, Toyota have already anticipated that, and the PWM shuts down. So, okay. Anyway, I started playing with the clamp meter here, and when I was commanding manual ID into the motor, what I would see when I had the meter on AC was you would get a spike of AC, but then it kind of settled down very, very low, like 1 or 2 amps. So then I put the meter on DC, and I'm seeing massive DC currents going in here. Now, it's probably my ignorance to how all this FOC stuff works. But I said, okay, I did buy this inverter as being broken. So, has it got a bad IGBT in it or something like that? So what I've done here is I've gone back and I put the original STM32 sine firmware in here. Put our clamp meter on AC current, and just using manual volts hertz mode, we can I'm commanding about 3 or 4 hertz into the motor at the minute. I'm seeing about 35 amps AC on all 3 of my phase leads here. And the motor turns, there's no problem there with that. There's no, at least much of a measurable DC component there on our meter, and that's a very stable, it's saying 34.5 amps here. And if I look at it on the plot here on the computer, it's within 1 or 2 amps of the of what it says on the clamp meter. By the way, this is the clamp meter that quite a few people have claimed was wrong when it reported that the Gen 2 inverter could handle over 300 amps per phase. So no doubt the 350 amps per phase that I'm seeing here is incorrect also. That being said, I think if I had a bad IGBT in here, I don't think the motor would be rotating smoothly. I don't think we'd have a nice stable current on all 3 of our phases here. So I think, at least I hope, that by running it just open loop mode here, we can prove that that we don't have a inverter hardware side problem. So I'm going to stop that. What I'm now going to do is I'm going to go back and I'm going to update, going to change back to our FOC firmware, and we will try the same thing, which is in this case manual ID, and just see again if we get this strange behavior here. I've been playing around with the various parameters. One of the things that we can, I guess, see is that the resolver seems to have 3 lobes on it. Now I'm not sure what that translates into for pole pairs, but I have it in as 3 pole pairs at the minute. So let's go back to that. Okay. Apologies for the power supply noise here. I'm busily capacity testing the 64 calb cells that I've removed from the E39. We will be publishing the data on that once we have it available. So our pin swap is in here, so everything should be good to go. So okay, we have FOC firmware back in. Now start in manual mode here, we're on resolver. So I got pole pairs 3 for the motor, no idea whether that's correct or not. Resolver pole pairs 3 also. Again, no idea whether that's correct or not. Now, what I'm going to do is I'm going to go into the manual ID parameter here. I'm going to command 10 amps, going to press enter. So what I've seen here is I've seen the current pop up to about 10 amps. Now it's dropped down to 1.2 amps. Now that's AC. If I flick my meter to DC, I'm seeing 8.5 amps DC. Now is that supposed to be like that? I don't know. I don't know enough about the operation of field orientated control to even know. In fact, the video that Johannes made on it there only a week or two ago was kind of the first explanation of this that I was actually able to follow. So that'll kind of tell you the brain surgery that's going on here. So it looks, yeah, it's kind of weird. Don't know about the motor parameters. I've scoped the resolver sine and cosine now. They're quite clean. If we graph angle on here, I can sometimes get the motor to jitter around, obviously completing full rotation of the stator. And we'll see it swing from 0 to 360 degrees and back again. So I don't really think we have a signal integrity problem here. We could have, but I don't think so. Let me show you what happens. So I'm going to just stop that there. Let's stop that inverter. And I'll run it in closed loop mode, or at least try to. So that's closed loop mode. Grab the throttle pedal. And we can, as I push the throttle, we can see the you can see it kind of jerking back and forth a bit there as I push the throttle. The whole assembly shakes. I've been, I can do stuff like I can start smacking the throttle like this, and we can get it to, kind of jump around the place a bit. But that is about the best that I've been able to achieve so far. During that, as I say, if we plot the angular position of the rotor as it's being received from the resolver, we do see rotation. The jitter, stationary jitter, is about 1 or 2 degrees. It's probably, actually let's have another look at that just while we're here. So I think what my next move is going to be to try a different motor, at least one that I know how to spin. I did have to come into this with the one motor that I had no idea about. Oh, silly me. Plotting the wrong thing, Damien, live on camera. Nothing like plotting the wrong thing. I'm plotting amp instead of angle. We don't want amp, we want angle. Rotor angle, please. Start plot. Okay, so I'm jittering right now, just stationary here. I'm jittering between Let's see, oh, we just got a big kick there, but it's sitting there now. There's virtually nothing going on there. I've got a flat line. But interestingly, just sitting there with no throttle applied. I think I'm going to make a liar of myself. I've seen a few spikes down all the way. It's sitting at a little bit over 350 degrees now. And I'm seeing spikes going down to 0 degrees there. So that's not a good sign. So let's increase our supply voltage a little bit, which will increase the amplitude of the exciter. Now if we press our throttle, and even just holding throttle fully down there now, there's a flat, I'm seeing a very slight motion on the what are you doing, Elon? Whoa, what are you doing, Mr. Musk? This isn't... It's almost like there's a kind of saying, come on, go, more gas, more gas. Wow. So I'm seeing rotation. It's actually rocking back and forth. I can see it on the graph here. So I don't know. It doesn't look to me like we have a signal integrity problem. That's the main problem here. I think there's probably something else going on. So yeah, as I say, we can, I can kind of pulse it a little bit, and it's knowing some more of the parameters about the motor, particularly the pole count versus the resolver pole count, I suspect, is going to be what we need to do. So that's it, folks. That is today's failure to communicate, or in this case, failure to spin. I hope you haven't enjoyed this as much as me. Hopefully, when we come back to you in the next episode here, we'll have this guy running under some kind of throttle control. But until then, do not forget to dislike, do not share, and unsubscribe yourself as quickly as you can. And check those links in the description for the usual suspects. And as always, happy Model 3 drive unit field orientated control motor algorithm spinning.